Hello, everyone. I've already been presented, so I will go very quick. I'm a passionate software engineer, in fact, and I worked on many things. I'm 55 something, so I did many things. I already been introduced. Lately, you see from the crabs, I've been working in Rust full time in my last 2 jobs. So it says, why are you in a JavaScript conference? I don't know. I'm here. So this talk actually already happened in TSConf 2019 Desenzano. I did it with a colleague of mine of the time, Gianluca Carucci, and the talk was not recorded. So anyway, this is your only chance to actually see it if you weren't there. And what actually happened about this talk? So why did this talk happen? Because me and this colleague of mine went with conversations like this. He asked, aren't these abstractions amazing? Like he was really into functional programming and all those complex things. And he was presenting me pieces of code saying, hey, these are amazing. And I replied, yes, but how much do they cost? And then we started talking, arguing, understanding what we meant to each other. And this is literally how the talk was born. So abstractions, the simplistic way. So something you can just think out of the box. Using abstractions, software is easier to understand. The idea is as if you apply an abstraction, it is clearer. Clearer means easier to understand, which means more maintainable, less bugs. And this is good. So let's use more abstractions and then, of course, profit, because every plan needs with profit. That's the point. And that's exactly the point, actually. So the very short version of this is it's not that simple. That's it. Now, why? To understand why it's not that simple, let's take an actual example, a small piece of code. It's intended to model a library order workflow. So you have an order of books, which is a list of books, which each book has a quantity. So it's an order, like a shopping cart. You have to validate it using an external service because maybe the warehouse doesn't have the books, something like that. And then you have to place the order, actually computing the price, and you have to compute it yourself because you could apply discounts, something. So it's really something that needs to be done. And then the game rules in this piece of code is that each operation is async because this is like a piece of microservice code. So you're expected to wait for replies. And each operation can fail because this is the real world. Shit happens. And the result of the workflow is the total order cost. So this is the end goal. You need to have the total cost so that you can place the order. This is how you could implement in plain async TypeScript. It's just code, you invoke the order service to get the order. If there was a problem, you return successful, so that didn't work. Then you invoke the validation server, and if there was a problem, you again invoke this. And at the end, you invoke the last service, place the order, and return it. This is pretty straightforward. Everybody should understand it very easily. Now let's start introducing abstractions. And the first thing is, it's a big name, it's a mouthful, monadic composition. Anyway, do you notice those error handling blocks in the code before? They are repetitive, they're line noise. They really get in the way. You try to follow the code and you are distracted by all these pieces. Wouldn't it be nice if you could throw them away without using exceptions? I'm not going to open this parenthesis. Exceptions are not a nice thing in this talk, sorry. So the idea is, couldn't we just compose them properly? Handling effects like an out-of-band channel. And it's actually possible using appropriate libraries and, let's say, conventions. So there is an effect library, which is modeling code that has effects. This is a functional concept. And if you use this library, this piece of code is the same thing as before. You have essentially an asynchronous pipeline that you are building on the outside. You are invoking it starting with the first argument, which is the order key. And then you invoke the 3 services, composing them. And the idea is that in this composition, the errors are handled appropriately and everything flows properly. So this is the way you think about the code. You compose things, put them together. This is an application of an abstraction. There are other libraries. There is an older library by an Italian, Giulio Canti, very smart man, called FPTS, Functional Programming in TypeScript, which does mostly the same thing, and now is discontinued because it conflated into effects. This is an example using FPTS. It's the same thing. So applying the same abstraction with a different library. Now, there is another abstraction we can think of using types. We just had an amazing talks about types. The type state pattern. Now, the idea is this. Consider again this error handling logic. There is the if condition in the middle. You could forget it. So this could be brittle because the idea is that if you forget that condition, when are you going to catch the error? You just forget to write the line. And the order is still the order. You got the order, you validated it, and then you place the order. The object of the order is just the same object. So if you forget the validation step, what is going to catch this? Now, the idea is that to encode the fact that the order must be validated in types. So if validation generated a validated order which has a different type, then place order service needs to require an object of type validated order. Then if you omit the middle section, the order object has the wrong type, which means that place order service is not compiling. Without even writing a test, you get the error. So this is another abstraction that you can apply, which can be useful. And so the code with checked TypeScript is just the same as before, because of this, it just works. Okay, so far so good. We had a few examples of abstractions, and do they look nice? I mean, do they improve the code? They could. I mean, if you think in terms of the abstractions, the code is clearer, but the answer for me remains, do they cost us anything? And what this does even mean? Do they cost us anything? Now, to define this, let's define a few terms. So I showed you the code first, but now let's think about the meaning of things. First definition is abstraction. What's an abstraction? Let's say that it is a high-level construct that can replace many low-level ones. So you can synthetically, in a single shot, capture something more complex, which should make the code clearer. An uncontroversial example, by the way, structured programming, we take it for granted. Once upon a time, it was not. Now, we would never write spaghetti code with gotos everywhere. But once upon a time, writing something like if then else was considered an abstraction. And for us, it's uncontroversial now. Nobody would ever go back to that time. Another definition, maintainability. It is how easy it is to change a piece of software without introducing bugs. And it's correlated to clarity. So if a piece of software is clearer to understand, it is more maintainable. And it is negated by complexity. It is very complex, it is less maintainable. This is the idea. Cognitive overhead. This is a double word. Cognitive means related to something you know. Okay, so there is a bit of etymology related to the Greek gnosis, whatever, and overhead is this extra quantity that you do not want. So a cognitive overhead is something you must keep in your mind, you are forced to think about it, and you would not want to think about it. This is my definition of cognitive overhead. And software performance, well, efficiency is using resources. Usually, it is better if software uses less CPU time and less memory. That is easy to understand. And cost, well, cost is something you lose to obtain a result. Usually money, also time, but we just know that time is money, so it doesn't matter. Cost is money in the end. So we have these definitions, abstractions, maintainability, cognitive overhead, performance, cost. Now, what are the consequences of applying abstraction? Well, in maintainability, I would say usually it's good in principle. So if software is clearer, is more maintainable, it's harder to introduce mistakes, everybody should be happy. I fully agree with this, normally. Problem is cognitive overhead. So Does everyone in your team understand the abstractions? Do you understand them properly yourself? How does it cost you to learn how to understand them? Now, I put here a flat smile and a minus and a plus, because the point is that this is also an investment. So in principle, you could say, today I don't understand it, but if I learn about it, I will understand it for the years to come. Which means, yes, it's a cost I pay now, but this cost is an investment. So it's very hard to judge in advance if the return for investment is appropriate or not. It's a mess, which means I'm not going to talk much about cognitive overhead. This is probably one of the most thorny pieces, but it's really on a case-by-case basis. Depends on the culture of the team, the knowledge of the team, how much they are willing to learn. It's very hard. And then there is performance. And here we said, what? Do we know the end result? Which means that we cannot measure the overall cost right now. Now, as I said, cognitive overhead is tricky, but we can measure performance. So let's just try to do it and see what happens. And measuring means we can benchmark different implementations of this simple piece of software, which is very simple, but actually realistic. We record all the execution times in microseconds and plot them. And the rules of the benchmark is we use 100,000 orders in the benchmark with 20 key orders of warm up to let the JIT optimize the code and everything so that everything is working properly. We inject a 5% failure rate so that we also test the error handling code. We also benchmark the performance of the error handling code with a certain percentage, so we try to be fair. And then take the mean execution time in microseconds. Actually, what I did was to run each benchmark 4 times and take the minimum. To say, okay, there could be noise in the machine, I just take the minimum. This was the thing. And I was executing TypeScript code with Dino 2.3, just because it was simpler. I had TypeScript, I would just run it immediately, and it uses V8, which is reasonable performance, so that was fine for me. And the implementations I tested, just to try to understand what was going on, was first of all plain async code. So no real abstractions, just the plain code you saw at the beginning. Then code done with defects, the functional framework. And then, because it was funny, I did the talk in 2019 with FPTS, and I benchmarked it. But then I upgraded to the newer version of FPTS, and I saw that it was different, so I also benchmarked that. The code was totally identical. I just changed the version of the dependency. And also FPTS with type state pattern. That's another abstraction, so it's a different benchmark. This is what I did. And this is the result with TypeScript. Is it any fast? So the vertical axis is in microseconds. So 2 microseconds, the first implementation. And the idea is that if we apply the effects library, we have about a 3x slowdown. If we just use FPTS 2019, we have a 2x slowdown. And for some reason unknown to me, forgive me, I didn't want to debug this performance problem. FPTS 2025 version had this amazing 5x slowdown, which I don't know where it comes from. I'm not bashing the thing. I'm just saying this is what I measured. By the way, the type state pattern had no effect. I mean, using the type state abstraction or not using that didn't really mean anything, which is sort of expected because types are mostly erased after build time, so it doesn't really matter, which means just use types. It's not a problem. The problems are the other things. So this is what happened with TypeScript. Summary. Abstractions do have a cost. We can see that. It's a micro benchmark, but it doesn't lie. Does it matter? Well, in a front end, I must say likely no, because if you need to evaluate this piece of code in a front end, if it takes 2 microseconds or 10 microseconds, I don't think it makes any difference at all. Now, in a backend, I would say likely yes. In my opinion, it should matter because in principle, you would pay more for your cloud costs if you take more CPU time. So it should really matter. Now I'm asking myself a question. Could these abstractions have 0 cost? Why are they costing us so much? Is there a way out of this thing? And well, 0 cost abstractions, they are popular in other languages, mostly C++, Rust, Zig. What does it mean, 0 cost abstraction? Well, I take the C++ definition, and it is honest because it is not really zero cost. It's zero overhead. It means what you don't use, you don't pay for, and what you do use, you couldn't code any better. So the code is as good as it could be, despite being higher level. This is the idea of zero cost abstraction, meaning the abstraction is just as performant as you have written the low level code by hand. An example, filter map in JavaScript. This is a piece of code when you have an array of numbers and you invoke filter and take the even ones and then map them to their double. This is plain JavaScript. Now, this thing in Rust, how do you write it? It's very, very similar. You have the numbers, you apply filter with a lambda. The syntax is different, sorry for that, but you can squint and look at it and you see that it's a lambda with the argument and the modulus, and you can map it. And at the end, there is this collect, which says produce a vector. Now, what's the difference between these? Well, there is a world of difference. Because first of all, in JavaScript, filter produces a new array and map yet another one. And this is unavoidable if you apply it as is. If you don't want this, you have to introduce transducers, functional composition, because it becomes, it's not impossible, but it's complex. While in Rust, you can write essentially the same code, but what you're guaranteed to have is that you don't produce any new array at all. Actually, to produce the new array, you need the fourth line in which you instruct the code to say, collect this into a vector. Otherwise, it doesn't even allocate memory. Which means Rust is a language where you can use the same abstractions, but they shouldn't cost you. Now, does it matter? As I said, as usually it depends. If this server-side code, would you want to choose between maintainable code or WLOOKUT builds? This is a very hard choice. And sometimes you need to make this choice, which is not good. So let's check if this assumption about zero-cost abstractions in Rust is true. And so we ran the benchmark on Rust. Essentially, I did a line-by-line adaptation of the TypeScript code to see same rules as before with Rust, well, a Rust compiler, whatever, one of the latest, doesn't really matter. And this is the idiomatic async Rust code. It looks like the idiomatic JavaScript async. Error handling is radically different because Rust has monadic error handling by default. But that's okay, this is idiomatic Rust. Rust with explicit future code, like using promises and then with promise, you know, it's just the same as JavaScript. Rust with functional composition, when you say compose and compose the functions, you can see that. And the code with type state pattern is absolutely identical, of course, because types are invisible here. And this is the Rust benchmark. And if you look at the benchmark like this, it seems that abstractions do have a cost, because yes, they do. But if you compare this with the TypeScript one, the cost of abstractions in Rust is actually negligible if you look at how much they cost in TypeScript. And the performance also is radically different. Now, why is TypeScript so much slower? Can we investigate why? And then I went on an investigation route. So essentially, I wrote a lot of micro benchmarks starting from plain synchronous code. So the same code as before, but without async. So to say, okay, how much CPU is this going to take just to compute the values? And then synchronous code, but using callbacks to see if this would add the cost. And then using FPTS, but synchronous. And then asynchronous code, but without promises, using callbacks, and then using async. And then using effects and FPTS and so on and so forth. So all the possible variations. And this is the performance graph you get. And so you see that synchronous JavaScript is actually really, really fast. Adding abstractions is, okay, things blow up. And the fact that there is the Node.js event loop doesn't help. So when you switch from synchronous to asynchronous, the fact that you are switching from your code into inside the runtime to evaluate the event loop, the promises, and then back into your code is adding a 4x slowdown. Just this. So this is one of the reasons of the differences in performance. And then I did all the same Rust benchmarks, essentially, again, all the implementations, and you can run them. And here you can see that there is a bit more difference in performance, but then again, you plot it against the TypeScript and it's the same as before. So when you are fully synchronous, they are quite close to each other, but when you apply abstractions, performance totally diverge. And a question, was this fair? I mean, was this benchmark proper? Because after all, Rust compiles to native code, so there's no match. Of course, it's faster. It cannot run in a browser. So we are not really comparing. Okay, in a backend, it would be fair, but in a front end, you can't. Or can it? Well, it turns out that it can. You can compile Rust to WebAssembly. So since we can compile it to WebAssembly, it's like adding another abstraction. So instead of having native code, you have code that can run on any CPU. You can think of it like an abstraction you are adding. So I tried to run the Rust code with WASM-time, which is a WebAssembly runtime environment. It was very convenient because I didn't have to modify anything. I just took the same Rust code, compiled it for WebAssembly, and ran it with a WebAssembly runtime. So it was just that simple. And this is the result of the WebAssembly benchmark. So again, you can see that there is a bit of a cost, a 2x slowdown overall in performance. This is what you get when you compare Rust native with Rust WebAssembly, which means that adding WebAssembly is about a 2x in performance, which is sort of expected fairly. But then this is the full benchmark result. So we have the flat Rust line at the bottom, which is the native one, the flat green one, which is the WebAssembly one, and the blue one, which is the old TypeScript one. So we can just see that just the very near synchronous part, they are very, very close to each other, which makes sense. But then if you start adding abstractions, things just blow off. So we are back to square one. We said, okay, we have maintainability, we are happy. We have the cognitive overhead, we don't know what to think about, but it's likely an investment. About performance, we are puzzled because the cost is there, but how can you avoid it? It's there. So how can you think about the overall cost? And then, as I said, cognitive overhead is tricky. We know that it can be a performance cost. We still have to decide if it matters. And I must say, I don't really have an answer that for everyone. We can reason about it. Now, this space that we are seeing is the graphs that I was doing before in a space with stars. And we can actually put a lot of stars. And the idea is that each one of these stars is one possible implementation that solves the given problem. So all those pieces of code, each one of them was correct. It did solve the problem. They are different solutions to the same problem. This is like the abstraction space. So we are in a space where you can choose, should I apply this abstraction or this other one with this language, with this other language in this environment, native code, WebAssembly. The space is huge. We can navigate this page and boldly go where no one has gone before, because this is literally exploration. This is what we do as engineers, by the way. As engineers, we need to find trade-offs. We have a problem to solve, and we need to choose the appropriate trade-off for the situation. So we are navigating this space and picking choices. What we really need to avoid, in my opinion, is tunnel vision. Now, there are many kinds of tunnel vision, and they are all biases. We could have a language bias. We could just say, I like TypeScript. I don't want to use or learn Rust. This is a bias that you think about in advance, and it conditions you. It is a tunnel vision. You are missing out on a part of the abstraction space. Or you can have a style bias. You can say, I love the clarity of functional programming. This is perfect for me. I'm happy over there. I would never want to write plain verbose code with async and error checking and everything. And again, this is a tunnel vision, a bias. You are missing out on a part of the solution space which could be appropriate. Or you could be nitpick, like I like async code. I don't want to write code with promises, or even the other way around. Why not? And so again, everybody has their own choices, their own way of tunnel vision. I would say avoid that. I would say actually follow the context. What does follow the context mean? It means understand the situation in which you're writing code, your problem, your actual requirements, and then it can be that performance doesn't matter. The team understands functional programming very well. Just go ahead, apply all those abstractions. It's fine. Or maybe not, and then you need to write in TypeScript, but in a more verbose way because performance matters. It's fine. Or you can afford Rust and WebAssembly or something like that, then go ahead, go there. The idea is that if you just follow the context properly, you will find the proper solution and everything will work out well. And that's all, folks. I will say thanks.